So welcome to this second in our series of Oxford Information Lab's lightning talks. Today we're going to talk about how software works. So to kick us off, the main, I suppose, high level point is, what does software do? And essentially you can think of software as taking some input from various different sources, whatever that might be, doing some processing with that input and doing some sort of calculations, whatever you want to be able to do, and then producing some outputs. And those of you that either lived through the 80s or into your retro films will recognize this character from Short Circuit, whose favorite phrase throughout the film was "need inputs." And of course, this is very much the heart of software. I mean, software is pretty much useless without inputs, and essentially just like robots need input to do anything, software, basically the fundamental starting point for software is some sort of inputs. Now input can take a number of different forms. There'll be some that we're very familiar with. So very common forms of input would be keyboard and mice. When we're entering data into, say, a word processor, we're using our keyboard and mouse. That's providing inputs to that piece of software. As I'm presenting now, the piece of software we're using for this presentation is receiving inputs from my microphone and from my camera, and is processing that as part of what we're doing as we speak now. Other sources of input for software would be more commonly known as data, or I guess information, and that would often come from either storage devices such as disks on your computer. These days, increasingly, we get data from databases, and more often in software from cloud and web services, which is the more common place to get data these days. So software will almost always be fed by input of one sort or another. That might be interactive input, as mentioned above, or it might be from other sources. But essentially, we're looking to gather some sort of input before we proceed with what we want to do with the software. And of course, the end of the story is that software is pretty useless without producing some sort of outputs. That might well be in the form of producing some output on the screen, for example, printing something out for you. We may well produce outputs in a form of audio. As I'm speaking to you and you're listening to me, software is producing output through a speaker at your end. Likewise, in much the same way and more commonly, software would tend to produce output in the form of writing data back to a database, writing data to a disk, and for example, saving a file in Microsoft Word would result in storing some data in a disk. And again, commonly these days, writing data back out to cloud and other web services. So essentially, you can think of software fundamentally as receiving some inputs and ultimately producing some outputs. And of course, the middle bit, that's the heart of software, is the idea of processing, and often we refer to that as programming. So at the basic level, a computer program is a list of instructions, or we often use the word commands, which operate on the input we've received and manipulate that input or data that's come into the system, and we produce some sort of outputs. That's the remit for a computer program. Programs are described using programming languages which are designed to be accessible to humans. So we're not aiming not to write our software in noughts and ones, which is a native computer language. We're aiming to write software in a manner that would make sense to humans and is comprehensible in some way. So here is my language pyramid to give you an idea of how sort of languages have developed. So as I mentioned briefly a minute ago, computers require us the software to be encoded in noughts and ones to actually execute at the lowest level. So whatever we write has to be turned into noughts and ones, and so that's always there in the background. But fortunately for us, over time, clever people have developed languages at higher and higher levels up this pyramid to make life easier for us. So the next level up is still, I've colored this in blue still to communicate the fact that assemblers are still very, very low level languages, but they essentially take the noughts and ones and turn them into some sort of way of writing and assembling software. But more useful beyond that are languages that start to actually become human readable. So starting with C and C++ are what we describe as building languages, languages that a lot of the infrastructure of computer operating systems and lots of the other languages we use are actually developed in sort of building languages like C and C++. And then from those languages are developed other languages, which we describe more as application languages. And these are the real heart of the language that we would use in OXIL Information Labs for developing applications. And as I say, these have been built upon lower level languages, but provide us with a reasonably comprehensible and human readable way of developing and developing software in a way that's comprehensible. And just to sort of make the point, there's an even higher level of abstraction at the very top, which I've referred to as embedded languages. And these are languages that are essentially run in a context of another program. So good examples would be JavaScript, which actually run inside web browsers, which are themselves pieces of software. And it's becoming increasingly common to have software languages running inside other software. So just to make the point that there's sort of like an ascending level of pyramid of languages, which get, as you go up the pyramid, essentially the software becomes easier and easier to write and easier and easier to understand as human beings. So that's just really a summary of where languages sort of fit in the hierarchy there. So what are the key abilities of a language? So as mentioned, fundamental to this is to facilitate input and output. We've mentioned already at the beginning that the most important thing is programs receive inputs, do some processing and produce some output. So a language needs to help us to gather the input we need and to then produce the output in whatever format we want to produce output. That's a fundamental key ability of a language. It's important that languages help us handle different types of data. So we may well be working with numbers if we're doing some mathematical calculations in our program. We might be working with character-based data. We often refer to those as strings, but chunks of text, for want of a better word. That's quite common these days. We're working with chunks of text. We also may be dealing with dates and times. We may also be dealing with simple true-false logic, and that's very common in these days. So to look at just very simple data types. So we want a language to help us deal with lots of different types of data. And then there's this sort of three, I would say, the real cornerstones of coding or writing programs, and that is the most important thing is an ability to support what we call conditional logic. And those of you that remember from school days, the obsession with drawing flowcharts in different subjects and also tree diagrams, that kind of thing. Programs are often represented very well with those kind of charts, because actually more often than not, as you're going through your processing, you want to make decisions. You want to say, if something is true, do this bit of code. If something else is true, do this bit of code. So very important to be able to have conditional logic available to us in a language. The other thing that's particularly important is what we call repetition, and that's to be able to apply some logic into lots of different items. So if you've got, for example, if you had a list of items you wanted to go through and do something for each item, being able to encode that logic once and repeat it multiple times is a very important aspect of a language and ability. And finally, we want reusability. Nobody likes cut and paste, let's be honest. It's painful, it's prone to error, and actually where possible, we want languages to help us to avoid cutting and pasting and to actually give us the ability to reuse wherever possible. So that's a summary really of what the abilities of a language when we're writing this sort of processing logic to deal with our data. Those are the key important things for us. So, I mean, other language features we'd expect to see in a language typically, as mentioned, we'd expect to have built-in functionality for providing access to resources for input and output. We'd expect to be able to very easily read data from somebody typing into a keyboard, or very easily be able to read from a file from a disk, or access databases and have those functions very available to us, so we can gather data for input very readily. Other very important concepts in languages is the ability to be able to store and retrieve data temporarily. So if you're involving yourself in some complex logic, you may well want to be able to store interim results that you're calculating and be able to access those. So there's a concept which is often referred to as variables, which is a means of being able to store data temporarily in a program. That would be stored. It would disappear when a program ends. It's temporary storage, but it's incredibly useful when you're encoding and processing logic to be able to store data temporarily for the duration of that process. Other things that you'd expect would be mathematical operations. A lot of what you do in programming is simple mathematics a lot of the time, and calculations. So you'd expect that, and also lots of other built-in commands to simplify things that you do repetitively. So these days, modern rich languages that we tend to use have hundreds of built-in commands, we call them, to help us and simplify lots of common use cases, so that you can really focus as somebody programming and writing software on the bits that are unique and that actually really matter to your use case. So there's nothing better than actually working through an example and actually to show you some code. So I thought it'd be good for us to do an actual example. And for today, we're going to use a very high level language, which is JavaScript, which is the language of the web these days. It's the language that is embedded in most web browsers. It's also becoming a standalone language in its own right, and is becoming very popular. And we use it quite extensively for ourselves in OXIL. So we're going to do a very simple example here. We're going to count through all the numbers from 1 up to a given maximum. We're going to go up to 10 for this example. And for each number, we're going to do the following. If it's odd, we want to be told it's odd. And we also want to work out the cube of that number, which for those who haven't done maths for a long time is the number times itself times itself. So if it's an even number, we want to be told it's even, and also to be told the square root of the number. So some very simple maths. So here is the output we would expect from that process. You can see there. So 1 is odd, and it has a cube of 1 times itself times itself. 2 is even, it has a square root of that long number. 3 is odd, it has a cube of blah, blah, blah. So you can see what we've got there. We've got an output here. We've received some input, which is actually, in this case, very simple. It's just the information that we want to derive the numbers from 1 to 10. And we produce some outputs here in a fairly simplified form. So now I'm going to go into sort of some actual code and how this would be encoded in a fairly human readable manner using JavaScript. So the first thing that we do, and this is back to a slide a few slides ago, I mentioned this concept of variables. We actually want to encode the fact for ourselves that our maximum value for this program is going to be 10. So we're going to count up to the numbers to 10. So I've actually assigned the number 10 to an actual symbol, which we've called max value. And this achieves two ends. The main end is that it makes our code below a lot more readable. We don't have to repeat the number 10 if we're using it many times. We can actually use the word max value from now on. And we know that's going to mean the number 10 for us in that context. So, and then the second thing here is the fact we're going to now loop through all the numbers from 1 to 10. And we're going to repeat some logic for all those numbers. As we mentioned earlier on, we want to be able to repeat and reuse logic. So this fairly human readable thing, this is a construct known as a for loop, which essentially creates another variable, which we're going to call I in this context. Those who have done any coding will know that I is the most common loop variable for this context. But what this line does here is actually says start I at the value of 1, keep going with I until we get up to the maximum value, and each time round add 1 to it. The plus means add 1 to the value of I. So what it means is repeat the next bit of thing I'm going to show you, repeat the logic for every number starting at 1. Whoops, sorry, I didn't see that. Starting at 1 up to the maximum value and incrementing by 1 each time. And this language, in common with most languages, encodes anything you want to repeat in these kind of braces here, so closing brackets. So whatever's inside this set of brackets I'm going to show you shortly will be repeated for all the numbers from 1 to 10. So let's look inside those brackets. So zooming in a bit more on that, what we have here is 2 use cases, and you can see that this idea of conditionality is very important. And in human readable syntax, we use the word if. And what this special thing here means actually is, this is what's called a modulo operator, but really what that's telling us, that statement, is that the I is even. So that's what that instruction there means, I is even. So as we count through the values of I, from the first time round, this is not going to be the case, because the first value of I is going to be 1, and therefore this whole next bit of logic here will not be run for the first value of I when it's set to 1. However, when I is run a second time round, so it gets to 2, this will then be run, as it's then an even number. So, and then once we've got into this, once that has actually fired, so if we're in the case of an even number, then we can actually go ahead and do what we want to do for an even number, which in this case is use a built-in function to work out the square root for us of the value of I, which would be, in the first case, would be 2. And then, of course, we can produce ourselves a message which contains the text and tells us that that number is even, has a square root, which we've just calculated using a built-in function. And this instruction at the bottom is purely a means of producing output. So the console log actually then will print out whatever the message we've produced higher up, and effectively gives us this output here, the line that you see there, 2 is even as a square root of blah. So what we've been able to do here is produce a loop. And just to go to the next stage, fine, and we won't dwell too much on this, but essentially what you've got is the other case, and we, again, using very human readable syntax, we have an if condition here, and we have an else condition here, which means if that wasn't true, then we do this one instead. So again, we're running the whole of this interior loop inside the for statement for every value from 1 to 10. Those that are even will be caught by the first block with the if conditional, and those that are odd will be caught by the even by the second block there with inside the else. And again, for the else, we use a mathematical function to work out our cubic for us, and we produce a different message which tells us that it's odd, and we print that out instead. So I'm not expecting the audience to necessarily have understood every bit of the detail of that, but the communication here is really that this is typical of all languages. We're giving ourselves the ability to repeat logic for lots of different items of data. We're also able to produce sort of flowchart type structures where we can conditionalize our logic based upon different values of data however we want to, and we can produce some outputs. So that's a very simple program which hopefully demonstrates some of the key aspects of programming. So finally, in summary, so I guess the key points to make are software is all about processing inputs and producing outputs. That's been the theme all the way through this presentation. Programming languages provide human-friendly, natural language, hopefully, in many cases, for encoding processing steps and logic. So we're able to write in a reasonably natural flow without having to get bogged down with machine code. And I think the final point to make is that languages are often built on top of other languages to produce higher level languages with easier learning curves. And the industry has very much evolved over the last 10 to 20 years to produce easier and easier languages to enable more and more people to be able to code and to produce effective software. So hopefully that's been interesting, and thank you for listening this morning. Thanks a lot.